Hello, this is the fifth video of Game Theory Series 2 for OCR Discrete Further Mathematics, and we'll be looking at the Nash equilibrium for other or non-zero sum games. In the previous video we considered these points to note that the Nash equilibrium can be found using the same method in zero-sum games or for non-zero sum games. That not all games have a Nash equilibrium, some games have more than one, and that the Nash equilibrium doesn't always give the best possible outcome for both players. Let's look at some examples to illustrate these points. Here is the matrix for a non-zero sum game showing payoffs as ordered pairs. So for example, we can tell it's non-zero in that if it was a zero-sum game, you would have a 3 and a -3, which you don't have. You have a 3 and a 4. So if player A plays strategy P and player B plays strategy X, A will win 3, but B will win 4. So let's check for the Nash equilibrium. If A knows that B is going to play X, then they will choose to still play P. And if they know that B is going to play Y, they will also play P. If B knows that A is going to play strategy P, they will play X, and if they think that A is going to play strategy Q, they will play Y. Therefore we can see that we have a Nash equilibrium at the 3, 4 or the Px. And this happens to be the best possible outcome for both players. Let's consider these further examples. So on the left hand side, again looking at A's choices when B plays X, that would be a 4, and when B plays Y would be the 3 or the Q option. B's choices would be to choose the X strategy when they think A is going to choose P, and the Y strategy when A is going to choose Q. Therefore, in this case we have more than one Nash equilibrium, both Px and Qy are Nash equilibrium, one of which, the Px, happens to be the best outcome for both players. On the right hand side, however, we would have that A would choose Q if they thought B was choosing X, and P if they thought B was choosing Y. However, B would choose X and -1 or the Y option if they thought A was playing Q. Therefore we can see there are no Nash equilibriums. Let us consider a scenario that was developed in 1950 by American mathematicians and called the prisoner's dilemma. Imagine you have two prisoners, both suspected of burglary, being held in separate rooms at the police station. Now the police don't have enough evidence to convict them of burglary, only enough to convict them on the charge of possession of stolen goods. And the police obviously think they did it, but want to put pressure on these prisoners to get a better conviction. So the police are going to try to convince each prisoner to confess to the crime by offering them a get-out-of-jail-free card. So they would not then receive any time in prison, but their accomplice or partner would be sentenced to a 10-year term. Now if neither of them confess, then they both will be charged with just the possession of stolen goods and receive a sentence of just 1 year in prison each. If both prisoners confess, then each of them will be sentenced to 5 years. And the police make sure that each of the 2 prisoners know that the other one has been offered the same deal. So here we've set up a payoff matrix for the situation. So if they both confess, then they both get 5 years each, which is seen as a negative. If either one confesses and the other doesn't, then depending on the one confessing gets no prison time and the other one gets 10 years. And if neither confess, then they each get 1 year. And we want to see if there's a Nash equilibrium for this game. What will the prisoners decide to do? So, looking at player A's decision, if they think that their accomplice B is going to confess, they would choose the least worst option. If they thought that their partner in crime was going to hold strong and not confess or not rat on them, then they would choose to confess themselves and not serve any time. Let's look at it from B's point of view. They would have the same decision. If they thought their partner was going to confess, they would also confess. And if they thought their partner was going to hold strong and deny everything, then they would choose to confess and send their partner down. As you can see, the Nash equilibrium then is this both of them to confess. Hence, given a rational, self-interested model, which we don't necessarily assume that criminals will be either rational, and they may well have great loyalty to their partners in crime, but if they were both rational and self-interested, then both of them would confess to the police and get 5 years each in prison. So it's a stable solution, because if either knew the other would confess, they would not change their strategy. But we need to note it is not the best mutual outcome. This here, 1 year each, would be the best mutual outcome. And so that's rather interesting. However, of course, this scenario cannot take into account the 2 prisoners' emotional reaction, or their past relationship, or the fear of retribution, and so on. This is the last video in the Game Theory 2 series.